we're going to be discussing acid-base reactions. We've already looked at some examples of these, both in class and in lab, okay? But here, we're going to discuss this a bit more and add some definitions, as well as adding a new way to think about what's happening when an acid dissociates. Okay, so let's begin by saying that when we have, I want to go ahead and give us a definition here. In fact, we're going to have a set of two definitions. So let's make some space over here, and we're going to, let's use a new color too. We're going to say that an acid is a species that when it splits apart in water produces H+ ions. Now, this might take a second. Sorry, sometimes I can't speak and write at the same time. This might take a second for us to wrap our heads around, because this is a very specific definition of an acid that doesn't really have a physical intuition, right? We're used to maybe thinking of an acid as a thing that eats away at something, right? But when we talk about this definition of an acid, we need to take that concept and put it out of our mind for a second. It's not that it's wrong per se. I mean, many acids do have that property, but what's happening when that happens, when you put an acid on something and we observe that it's eating away at something, what's happening is this chemical reaction where the acid is producing H+ ions, and then you have a reaction between the species of that acid and whatever the thing that it's reacting with, okay? So we need to put that out of our mind for a second so that we can hold this new definition. We're going to have two complementary definitions here. An acid is going to be a species that produces H+ ions. A base is going to be a species that produces OH- ions when it dissolves in water. Now, to be honest with y'all, this is kind of a simplistic definition of acids and bases, but it's going to serve us pretty well for quite a while. Okay, later in this course, I think it's this course and not the next one, we will have some more sophisticated definitions of acids and bases. Really, all I mean here is that they add a little bit more detail, and then from there we'll be able to see how they kind of reduce back to these definitions. Okay, but this is what I want us to think about for now, is that an acid will be a species that produces H+ when it dissociates in water. So for example, let's look at HCl, right? We know that when we put HCl, hydrochloric acid, in water, it will split apart and form two species. One of those is H+, the other is Cl-, okay? But already we can see how this fits our new definition, which is to say the Arrhenius definition. So let's say these are the Arrhenius definitions. This is named after Svante Arrhenius. Okay, so these are the Arrhenius definitions of acids and bases. In other words, these are one way of conceptualizing what the effect of an acid and what the effect of a base is. What is an acid? It's a species that splits apart and produces H+ ions. What's a base? It's the species that splits apart and forms OH- ions. So let's look at an example of a base. Okay, well, one of our strong bases, sodium hydroxide. When we take this and we put it into water, it's going to split apart into two species, sodium+, which is in aqueous format, and OH-. So now, hopefully we see why we characterize sodium hydroxide as a base, at least according to the Arrhenius definition of a base. Because when we put NaOH in water, it splits apart, it ionizes, and it forms OH- ions. Okay? Now, I want to call attention to a kind of subtle detail. And this idea is that when an acid splits apart, it forms ions. Okay, what do I mean by that? Let's take as a counterexample sodium chloride. Okay, so let's grab a new color here so that we don't think of this as part of the previous section. Oh, I gotta get to our paintbrush. Okay, I want us to make a small distinction here between ionic compounds and acids. Okay, so let's just abbreviate that as CMPD. And in fact, let me say versus acids. So let's look at two similar species here. One of these is going to be sodium chloride, okay? One of these is going to be hydrochloric acid. I want us to distinguish something between these two. This species, let me grab a new color. This species is made of ions. Why do I say that? Because sodium chloride, right, if we think back, let's see, give me 1 second here. I think I've got that picture saved in my Western folder somewhere. So this is the one we just worked through here. One thing we talked about in here, oh goodness, where is it? Oh, I guess it was way up here. Yeah. So one thing we talked about in this first picture is the idea that sodium chloride is composed of a lattice, okay? It's composed of alternating charged atoms, right? The Cl's here are all Cl minus. The Na pluses, or the Nas are all Na pluses, right? We have positively charged sodium cations. We have negatively charged chlorine anions. Okay, that's different from what we have in hydrochloric acid, though. Let's go ahead and redraw that picture over here. Okay, so over here with sodium chloride, we're going to say that we have this lattice. And actually, I haven't really drawn it this way, but I want you to remember that this is three-dimensional. Okay, so this actually, let me draw one extra layer back here. Now we'll draw our chlorides. Oh God, I'm not good enough of an artist to really pull this off. So this is a three-dimensional arrangement of atoms in space, right? Let me just go ahead and draw a box here so we can kind of visualize what's going on. Oh goodness. Kind of visualize what's going on here. Okay, so this is a three-dimensional repeating structure in space, and that's just the world's worst drawing. So in fact, I'll tell you what, I'm just going to go over to Google here and do what I should have done before. And now we see, albeit with a kind of, here we go, same color scheme, that this is a three-dimensional repeating structure in space, okay? So what I want us to remember, though, is that each of these atoms at these sites here are already charged. These sodium atoms, for instance, have already given up 1 electron each and formed Na plus cations. By contrast, these chloride anions here, well, they're already anions. They've already gained an electron from the sodiums, and so they're already negatively charged. That's not the same thing, though, as hydrochloric acid. In the case of hydrochloric acid, this is just a covalently bonded molecule, right? So we'll have a hydrogen and we'll have a chlorine. So we'll try and use some of the usual color schemes for these. And in this case, this is just covalently bonded, right? There's no ions currently present in this molecule. When it splits apart, though, okay, so let me be more clear. I'm to the right, I'm also going to draw out the bonding here. So this would look not like that. This would look like this. Okay, and I'm going to also put these dots on here so that if anyone recognizes these, they'll sort of know what's going on here. Don't worry about these dots here that I put if these are unfamiliar. Okay, it's really not something we need to know yet. I just wanted to draw this out so we can sort of see what's going on here. At first, each of these molecules, or each of these atoms, is sharing these two bonds here in the middle. And so hydrogen, let me use a different color for that second circle. Let me use a more different color. We'll use purple here maybe. It's maybe not as different as I hoped. But hydrogen here has these two electrons. So hydrogen has a full outer shell. Remember that hydrogen only needs two. Okay. Chlorine over here has a full outer shell. It has 1, 2, 3, 4, 5, 6, 7, 8. The bond here counts for 2 electrons. Make a quick note of that. Okay. So each of these elements has a full outer shell, and they're not ionized. Right now, the hydrogen and the chlorine are sharing those 2 electrons in the middle. But when this molecule splits apart, it ionizes, it forms ions. So let me do a better job of that. When this splits apart, you actually have an H plus and a Cl minus. Okay, and in this case, this is a chlorine that has an extra electron. And this guy over here, well, this is a hydrogen that has lost an electron. But let's zoom in on that for a second here. Let's add some context here. A hydrogen atom usually, so let's say this is this one right here would be a hydrogen cation. But let's take a second and look at a neutral H atom. Well, most hydrogen only has a single proton, 0 neutrons, and a single electron floating around it. Let me label these things. Okay. So now that I've done this, right, what happens when we have an H plus ion? What happens when a hydrogen atom gives up its electron? It's just a proton. That's all that's left. Right? This would look like this. So we could say that we've got a proton with an empty shell around it. Let me just go ahead and put that dot over here too. We could say this, where the hydrogen has no electrons around it. Let me make that a bit more clear. I want to make sure I don't make it seem like there's anything there, which is the same as this. Okay, so what I'm going to say is that H plus is just a proton. And in fact, chemists kind of have a tendency to just think of H plus as being a proton, because it is, right? It's nothing more than just a bare proton, not a protons. Okay, so as a result of that fact, we have a tendency to say that H plus is what we call a bare proton. Okay. So we can also go back up here and just think for a second and say that an acid then is a species that produces protons when dissociating in water. Okay, so now that we've said that, let's talk a little bit about some types of acids here, not strong and weak, but polyprotic. Now what do I mean by that word? Okay, poly in this case, of course, just many, but protic here. So let's say monoprotic and polyprotic acids. The protic part just refers to protons. Okay, so let's say some acids only produce one proton when they dissociate in water. Now, what might some examples of this be? Can you think of some acids, I'm going to finish writing this, can you think of some acids while I do that, that would only have a single proton to give? And feel free to pause this and take a second, because I'm about to give some examples. No need for a question mark there. While I finish writing this out, feel free to pause if you'd like, and skip ahead when I'm done, because I'm going to give us some examples once I finish writing this next sentence of monoprotic acids. So what might some examples of this be? Well, how about HCl? When that splits apart, we get H plus and Cl minus, just a single proton for each. We get 1 mole of protons for each mole of HCl. We get 1 single proton for each single HCl molecule. Okay, how about some other examples? Well, we could also have nitric acid, because when this splits apart, we get H plus and nitrate. Okay, how about one more? How about a weak acid? Well, what about acetic acid? Okay, so when this thing splits apart, remember, in fact, let me be more careful here. Remember that this is actually going to be a bidirectional reaction. So I'm going to write this one using a forward and backward arrow. We don't usually write them vertically like that, but it's the format I chose for some reason. So when that splits apart, right, we're going to wind up with protons and acetate anions. But we're only going to end up with a single proton for each of the acetic acids that dissociate. Remember, because acetic acid is a weak acid, most of it's not going to dissociate. But for each molecule that does, we're only going to get 1 proton. Okay, cool. So that's what a monoprotic acid is. Now, we can also say that some acids split apart multiple times. And each time, it's sort of like a different cost to split it apart. We call these types of acids polyprotic. Let me go back to red. So what are some examples of this? Well, feel free to take a second, okay? I want you to think about it just for a sec. Feel free to pause. I want you to think of some examples of acids from what we've talked about that have more than 1 proton to give. I'm going to go ahead and jump in here. So if you want a second more to think, go ahead and pause. Here are a couple examples for us. Well, one of these could be sulfuric acid. Right? When this splits apart, now I'll actually do it horizontally the way I should have the first time. We're going to split off and form a single proton the first time this ionizes. Okay? This also then will leave behind another polyatomic ion here. Right? So this is not going to be sulfate in this case. This is going to be what's called hydrogen sulfate or bisulfate. I'm going to go ahead and just label that for us so that we can start familiarizing ourselves with those names. Let me pick a new color here. So this thing, I'm just going to go ahead and call this bisulfate. Okay, well, what happens now? Bisulfate itself can split apart. So we can have HSO4 minus split apart again into H plus. And, well, we know this species, right? This one's just sulfate. So an acid like sulfuric acid is going to be considered polyprotic, diprotic, in fact, because it has 2 protons that it can give. So let's switch back to the other red here. So we're going to say that this one is diprotic. How about one more example here? Well, I'm not going to show you all the steps that happen for this one, but I will go ahead and tell you about the example of phosphoric acid. We know phosphate, right? We know that phosphate is PO4 3-. So phosphoric acid, the acid that forms from this species, from this polyatomic ion, is going to be H3PO4. Well, what would this look like? We can actually have this split apart 3 times. Okay? Yeah, let me go ahead. I will just go ahead and write this out. And this time I'll include our phases just for completeness. Okay? So let's see. I'm going to assume that these are, I can't remember if phosphoric is strong or weak. So you'll see me look this up while we do this. Yeah, okay. Well, it's not on our list, so we really should have predicted that, right? So the first time that this ionizes, we're going to have this split apart, and let me add a double-sided arrow to remind ourselves that this is a weak acid that only partially dissociates. Okay. So the first time that this splits apart, we're going to be left with a single proton, and then this polyatomic ion. So I'm just going to go ahead and salt our table here. If you look back at table 3.4, you will see that this one is hydrogen phosphate. And in fact, let me go ahead and put up here the alternate name for this, which is hydrogen sulfate. So this guy here, hydrogen phosphate. Right, but now hydrogen phosphate can split apart again. And in fact, I should have 2 hydrogens there. So sorry to everybody who is sitting there like, why didn't you put 2? So this would actually change this species. My apologies here. Let's go ahead and clear that out. And in fact, I'll just take this whole thing, move it over a little bit. Yes, if you're sitting here like, what are they doing? Yeah, you're right. That should be H2PO4 because only one hydrogen has, well, let me be more careful. Only one proton has split off from this molecule. Okay, so this is actually, we're going to name this one H2PO4 minus. Goodness, I was just jumping way ahead. I was thinking about the next step here. So this one should actually be H2PO4 minus. We're going to call this species dihydrogen phosphate. Okay, it is a polyatomic ion that you'll be able to find in table 3.4. But let me think on it a minute before I decide on whether I have you memorize that one. Now, dihydrogen phosphate can split apart as well. Okay, so we could have this species ionize a second time, and this one would form H plus, a second proton compared to like a second proton that has come from our original phosphoric acid now, and here we would have hydrogen phosphate. So this will be HPO4 2 minus. Now, let me label it, and we'll go through and talk about that very last ionization step. I'll close that other parentheses in a sec. Okay, one more step of this reaction, though, we could now have that hydrogen phosphate split apart one more time. Okay, so now what we would have is a third proton that has arisen from our original phosphoric acid molecule, and we would have an ion that hopefully we recognize, which is to say phosphate. So in this case, we would consider phosphoric acid to be a triprotic acid. Triprotic because we can get 3 protons out of it. Okay, cool. So a little bit more here. The other things I want us to talk about will be the ideas of acid-base reactions, which we've talked about a little bit in class already. But we're going to talk about that and then talk about the idea of titration, something that most of you have done now in lab. And we're going to talk about that a little bit conceptually and then quantitatively. Okay. So, put a new section in here. These are also sometimes called neutralization reactions. And the reason they're called this is because we call a solution with an excess of H plus ions acidic, and we call a solution with an excess of OH minus ions basic. Well, you have probably heard about the pH scale. We will talk about this in more detail later in the course, but this measures acidity, right? It measures how much H plus is in the solution. The more acidic something is, so we're going to say pH less than 7, we're going to say that this is acidic. Something with a pH of greater than 7, we're going to say it's basic. Okay, so something that has lots of H plus ions is going to be acidic, and it's going to have a pH of less than 7. Something that has lots of OH minus ions is going to be basic, and it's going to have a pH of greater than 7. But something that has a pH equal to 7, or very nearly 7 at least, is going to be what we call neutral, right? Where is my cursor here? Okay. So in this case, what we would say is that the H plus, the amount of H plus, is roughly going to be equal to the amount of OH minus. So we call these a neutralization reaction because it makes the acidity of the solution neutral. Okay? Well, rather, it gets rid of the acidity or the basicity, I suppose, of the solution. Okay, so let's look at a couple examples of this. Generally speaking, how this will look is that we have an acid plus a base is going to form some sort of salt. And we need to be careful. When I say salt, I don't necessarily mean sodium chloride. That is one example, but it's not the only example. And in fact, we call sodium chloride table salt because it's the most common salt that we use on our tables, right? So it's going to be any kind of ionic salt. Let me go ahead and specify that. Okay, so let's look at a couple examples of this. We've already seen a couple. One of our archetypical examples is going to be it's going to be hydrochloric acid plus sodium hydroxide. And of course, both of these are going to be aqueous. When we do this reaction, what we mean is that all of this is dissolved in water. But this is going to form a salt, right? It's going to form sodium chloride in this case. And it's also going to form water. And in this case, we can just go ahead and call that liquid, right? Water dissolved in water maybe doesn't make a ton of sense. So let's write this equation one other way so that we can get a picture of what's going on here. We now know that hydrochloric acid is a strong acid. In other words, what that means is that hydrochloric acid will pretty much 100% split apart into these two species. H plus ions, which we now know are just protons, and chloride ions. Okay, but we also know that sodium hydroxide is going to split apart into sodium ions and hydroxide ions. And why do we know that? We know it because it's also a strong base. So when this reacts, we've said that this forms this salt here. In fact, it forms table salt. But we know also that table salt will dissolve in solution. So we wind up getting Na plus Cl minus. And what are we left with? Well, this water here, water is just going to be water, right? And there may be a parallel reaction here where certain water molecules are splitting apart and splitting into H plus and OH minus, but then also they're recombining as well. So in this case, we're not even going to worry about that. We're just going to say that we get H plus Cl minus Na plus OH minus forms Na plus Cl minus plus H2O in liquid form. Every other species here is in aqueous form, and hopefully we can see that some of these species appear in exactly the same format on either side of the equation. So for instance, the chlorides here, it's pretty much, from what I can tell, it's like nothing changed about that. Those chlorides were there at the start, and they're here now, but they didn't really change format. And it seems to me also that these sodium cations did not change format either, right? What we could say here is that, okay, sure, we put the hydrochloric acid in solution and it split apart. And we put the sodium hydroxide in solution and it split apart. And then it formed sodium chloride and it formed water. But that sodium chloride just split apart too, right? So we could kind of think of it like, yeah, sodium chloride is probably forming in trace amounts constantly in this solution, but it's redissolving just as fast. So we're kind of left with the same situation as when the hydrochloric acid and the sodium hydroxide dissolved, right? It just left behind free H plus, I'm sorry, well, it did leave behind H plus, but it left behind chloride anions and sodium cations. And the same thing is true at the end because the sodium chloride just splits apart into the same things. So what we're left with overall, we could take out these species that are repeated. God, it's so hard to see my cursor on here. We could take out the species that are repeated here. And what we'd be left with is only those things that truly changed form between the beginning and the end. So let me rewrite this equation with everything that is not present removed. So we're going to say Cl minus aqueous doesn't change. So we're going to say, we'll just leave it out for now, okay? We don't have to leave it out. I mean, it's helpful sometimes to get a picture of what's going on for sure, but sometimes we want to know what's actually changing state in this reaction. So what we can say is that these two species, be mindful, when I write this, I tend to do a hook on my Q's, but this is not Ag, this is AQ. So AQ here would be for aqueous, meaning it's dissolved in water. Okay, a little late for me to say that, but here we are. These sodium cations don't change either. So let's take them out, and we'll just see what we're left with. Well, it looks to me that overall here, I have aqueous protons plus aqueous hydroxide anions, and that's forming water. It's just forming liquid water here. Okay? So the idea of this reaction here is that if we take out everything that doesn't change form, this is the only bit that's left. So let's label these things. We are going to call this first one, let's see, what did they want me to call it here? What does the book call it? The book calls this first one the molecular equation. Right, because what this is telling us is everything that's reacting, but in its complete chemical formula state. Okay, so this next one, though, it calls this the complete ionic equation. It's calling it an ionic equation because you see in this case everything here that either contains or forms ions is written in that ionic form. Okay, so for instance, the hydrochloric acid does not contain ions at first. These two atoms are covalently bonded, but when it goes in water, the water molecules interact, the negative charge in the oxygen interacts with the hydrogens in hydrochloric acid, and the positive charge on the hydrogens in water interacts with the negative charge on these chlorines. And so the hydrochloric acid will actually split apart, but in the process, chlorine steals the electron that it was previously sharing from hydrogen. Right? They were sharing 2 electrons. Chlorine is like, here's one of mine, and hydrogen says, okay, here's one of mine. But when these two things split apart, chlorine becomes chloride and steals that extra electron. Now H plus is nothing but a proton, and chlorine has become chloride with an extra electron. Okay, so the complete ionic equation includes the ions for this species, even though, hydrochloric acid is covalently bonded, but it ionizes in solution. The same thing is true with sodium hydroxide. Right? When this splits apart, we form a sodium plus cation and a hydroxide anion. And once more, the same thing is true for sodium chloride, although in this case, this species already contains anions. Remember, in this case, this is actually a lattice consisting of, let me not show you my not so great picture of it. If we go back over to when we looked at the sodium chloride lattice here, right, this is actually an alternating 3D arrangement of plus and minus ions. So this one already contains ions. But either way, we split apart both of these species into the ions they contain. And as a result of that, we can write out this full equation here. So this one here, we can write it in terms of the ions that it splits apart into. And we can then look and say, okay, which of these ions do not change form between the start and the end? And some of these do not change form, right? They're just sitting there floating around in solution exactly the same way that they were before we started. And that would be the chloride anions and the sodium cations. They're still present at the end, floating around, occasionally meeting up and splitting apart again, just the same way they were at the start. The only things that are not present at the end in the exact same form they were at the beginning is the H pluses and OH minuses from our hydrochloric and our sodium hydroxide. Right? Those two will combine and form liquid water, which in this case we're to consider as being separate from this reaction. When I say separate there, what I mean is that this does not reionize. Okay, and we'll see later that there's more complexity to that picture. But what I want us to bear in mind here is that the water that is formed from this neutralization reaction splits apart to a much smaller degree than the sodium chloride that is formed. That sodium chloride essentially does not form because it redissolves so quickly. Okay. Let's see. Let's look at perhaps one more example of this. And so actually what I'll do for this one is I'd like you to consider this as part of your quiz. Okay, so question 2 on your quiz. Let's go back over to this image, and we'll add this as question 2, and we'll work through this one together, okay? It's open notes after all, so I will talk through this one, but I want you to work through it and write this along with me. And in fact, what we're going to do is we're going to make this part 1. We're going to have a part 2 as well that will involve some calculations. But we want to talk about a few more things first before we do that. So a balanced acid-base reaction for, let's pick, how about we say nitric acid and calcium hydroxide. Now, I'm going to be very clear here that we want to include all of the phases in this reaction. When I say phase, I mean things like solid, liquid, aqueous, etc. Okay. Now back over here, let's work through that example. So we want to look at, let's just go ahead and copy that from over here. We want to look at this question. So the first thing we're going to need to do in this case is convert these names of species into formulas. I'm going to ask you to pause for a second and do your best to work through this acid-base reaction. Think back to how we said up here that an acid-base reaction will be, it will be an acid plus a base forming an ionic salt and liquid water. I want you to take a shot at this. Go through, try to convert the name nitric acid and the name calcium hydroxide into formulas, then go through, determine what you can start by, perhaps by saying, okay, let me form water, and now what ionic salt will be left over. So I'm going to ask you to go ahead and pause, give that a try, and we'll talk through it in a second after you unpause. Okay, now that you have taken a second at that, and if you haven't, please do go ahead and pause and try it, all right? I want you to get the feeling of giving this a shot before I talk through it. Now that you really have, let's go ahead and look at what this would look like. So nitric acid. The ic acid part indicates to us that this, and the fact that there's no hydro at the beginning, indicates to us that this is probably formed from a polyatomic ion. Which one? Well, if it's ic acid, it comes from 8, so nitrate. Well, let me grab our brush. So NO3 minus is nitrate, so I suppose nitric acid would be HNO3. Why just one H? Right, because a single proton is H+, NO3 has a single minus, so we only need one proton to cancel this out. And so what kind of acid would this be? Well, it would be a monoprotic acid. All right. So now that we've got, and let's be careful. Let's write our phase here. This is going to be aqueous because this is an acid-base reaction. It'll always be aqueous for these. Now that we've got our acid written out, how about that base? Okay, I'm all about it. So calcium hydroxide. Well, in this case, we have to first identify that hydroxide is OH minus. That's our first step here. Knowing that, we would also then take a look at calcium, and we need to know that that's going to be a 2+. Let me write that a little bit more clearly here. We need to be able to identify both of these ions so we can figure out the ratio that they combine in. If this is 2+ and each hydroxide has a 1-, I'm going to need 2 hydroxides in order to cancel out that single calcium 2+. So this is going to be Ca, and let's make sure to put this in parentheses because we need to double up on that entire hydroxide ion. This is going to be CaOH2. Let me say CaOH quantity 2. Okay. Also aqueous. Now, what's going to happen when these react? Well, I can first identify the water, perhaps. It seems to me like over here, I'm going to have an H2O. Now, how did I identify that from here? What I want us to do when we look at these kinds of things is mentally split these molecules in two, and we need to split them along where the ion is. So for instance, for this first one, I've got H and NO3. For this second one, I've got calcium and hydroxide. Okay. To form the water here, you can look at it like I took the hydrogen and the hydroxide and combined them. So to figure out what the ionic salt would be, I can take the other two species and combine them. So let's go ahead and write that out here, and then we'll clean some stuff up. So if I take all of this and combine it, well, I've got a calcium, right? And I've got a nitrate, and I'm first going to have to figure out what ratio they combine in. Well, if I've got 2+ on calcium and just a single minus on NO3, this is going to need to be calcium and 2 nitrates, right? So we're going to put the nitrate in parentheses and put a 2 around it. Okay, let's grab that guy here. I'm going to copy that and undo some stuff here, and we'll go ahead and paste that back here. Okay, so we'll just redraw that arrow over here. Now what's this last one going to be phase-wise? It's going to be aqueous. In fact, let's make a little bit more space for ourselves. And this is going to be the reaction, well, let's use our new vocab terms. This is going to be the molecular reaction. I'd also like us to go ahead and practice, after we balance this, I'd like us to practice writing out the complete ionic equation and the net ionic equation for this. Okay, so let's make sure that this thing is balanced. And it doesn't look to me that it is at first. The reason I say that is that it seems to me like we've got just a single nitrate here, but we've got two of them right here. So let's go ahead and start off our balance by just putting a 2 in front of this. And now what it seems to me is that I have 2 hydrogens over here. I also have 2 hydrogens here. And I only have 2 over here. So total on the reactant side, it looks like I've got 4 hydrogens. 2 from the nitric acid and 2 from the calcium hydroxide. So let me move over that plus a little bit so I can try putting in a 2 in front of the water, and we'll see what that does for us. Okay, so now if I take an accounting of everything, I've got 2 hydrogens plus 2 hydrogens on the reactant side. On the product side, I've got 4 hydrogens, so that checks out. I've got 2, well, in fact, let's just balance the nitrate as a whole thing. I've got 2 nitrates, and I've got 2 nitrates on the product side as well. I've got 1 calcium and 1 calcium, and then I've got 2 oxygens and 2 oxygens. So this equation now seems to be balanced. But let's convert this into a complete ionic equation. Okay, so this thing, the nitric acid, because we know this is a strong acid, this is going to completely split apart in solution. Right? It's going to completely split into, well, every 2 moles of nitric acid are going to split into 2 moles of protons, and we're also going to have 2 moles of nitrate. Of course, we're also going to have this strong base calcium hydroxide split apart, and we're going to get a Ca2 plus, and we're also going to get 2 moles of hydroxide. Now, everything on our reactant side so far has been aqueous. This one will be too, but what we see is that our entire reactant side is aqueous. Okay, so that gives us the reactants. Let's write our products down here. Well, now our calcium nitrate, this is also going to split apart. Now, how do we know that? Well, that's going to get a little bit into solubility rules, which we'll talk about in this next video. Okay, so I always lose track of that mouse here. Okay, so this species is going to be aqueous. How about the nitrates here? Well, we're going to have 2 of them here, so this is going to be 2 aqueous nitrate ions. Okay, likewise, these will be aqueous. And then here at the end, we're just going to have those 2 liquid water molecules. Now, let me put a little divider bar in here. This second reaction that we've written out is going to be the complete ionic equation for the acid-base reaction of nitric acid and calcium hydroxide. After this, we're going to identify the net ionic equation. So how will we do that? Well, remember, we're going to need to identify the things that are the same on both sides. Okay? So I'm going to underline these here so that it's not too intrusive. It looks to me like I have 2 nitrates that are the same. And it looks to me like I also have a calcium cation that is the same. So if I were to remove these things, in fact, before I remove them, let's give these a name, okay? These things are what we call spectator ions. These are ions that are basically just watching the reaction happen. You know, they're kind of doing their own thing. Sometimes they meet up with each other and react, but then they dissolve again just as fast, okay? So these ions effectively are not doing anything in solution. We call them spectator ions as a result. So we're going to take out the spectator ions when we write the net ionic equation underneath this. Let's put a couple more dividers in here. Now what are we left with? This will probably look pretty familiar to us, right? We've got the aqueous hydrogen, and I will put our numbers in front of everything in a sec. Now you'll notice that in this case, we can carry over these 2's in front of everything from the complete ionic equation. But now that we're here, of course, we don't really need to include them. We can, if we want, just to remind ourselves sort of where we came from with the complete ionic equation. But at this point, we could also say that the ratio of the net ionic equation is not 2 to 2 to 2, but rather 1 to 1 to 1. Either of these would be okay. Okay, now let's bring this idea home by talking about the idea of a titration. Okay, now we're pretty close to this idea already. We've already talked about how an acid-base reaction is often called a neutralization reaction. We call it this because it involves eliminating the excess of H+ ions or the excess of OH- ions, and bringing the amount of each of those to pretty much the same number, okay? So in other words, an acid-base reaction reaches the neutral point, right? We usually call this the equivalence point. So it reaches that point when the amount of H+ ions is equivalent to the amount of OH- ions, okay? So that point, that equivalence point, happens when we've neutralized either the acid or the base, right? Whichever one was there, and we were slowly getting rid of some of it, right? That's the one that we've neutralized here. That distinction doesn't really matter here. They're both neutralizing the other, okay? But so in this kind of reaction, you have one species that tends to produce H+, or in other words, tends to produce protons, and you have one species that tends to produce OH-. Okay? When these two species come into contact, the excess of one starts to cancel out the excess of the other, and you bring this whole thing back to neutral. In lab, right, you saw an example of this using a piece of glassware called a burette, where you were dispensing a certain amount of sodium hydroxide from the burette into a beaker with acid, with hydrochloric acid. Okay, we just looked at this reaction actually, in this case here, HCl plus NaOH gives NaCl plus H2O. That process there, the process by which you have an acid and a base reacting and canceling each other out, is called a titration. Okay, and in a titration, your goal essentially is to reach the equivalence point. Okay, the equivalence point, as we've just said, is when the amount of the amount of the H+ generated by the acid is equivalent to the amount of OH- generated by the base. So when we have that happen, that is what we call the equivalence point in a titration. We can formalize that a little bit. Okay, we can say that the number of moles of the acid needs to be equal to the number of moles of the base, or at least stoichiometrically equal. Okay, what do I mean by that? Well, in this reaction here, every 1 mole of HCl reacts with 1 mole NaOH. Okay, so we just need the same amount of each one. In some cases, though, right, as we saw down here, we would need twice as much nitric acid as we have calcium hydroxide. Why? Well, both of them are going to completely split apart, right? Nitric acid is a strong acid, and calcium hydroxide is a strong base. So each one will completely dissociate. But the calcium hydroxide, every time one of those dissociates, it produces 2 hydroxides. And the poor old nitric acid over here can't keep up on its own, right? One single nitric acid is only going to produce a single H+. So we need twice as much nitric acid as we have calcium hydroxide in order to neutralize them. So let's take a look at that. And I'm going to write this out as question 2, well, part 2 for this question on the quiz. Ooh. Okay, and we'll go back over to here to write this out. Let me save this. I will save this as acid-base reactions. Okay, question 2 here. I will say, how many moles of 0.5 molar, okay, so if you need to, please take a moment and pause and refresh yourself on what molarity is. Okay, so what I'm going to say is how many moles of 0.5 molar sodium hydroxide are needed to reach the equivalence point in a titration. Ooh, excuse me. In a titration with 0.125 molar HCl. Okay. Let me be a little bit clearer here. I am going to say I'm going to change just a couple of things here. I'm going to say instead of the number of moles here, let's make this what volume. Okay, we could have answered either one of these, but this one will have us think a little bit more deeply about it. So what volume of that is needed to reach the equivalence point in a titration with, let's say, 150 milliliters of 0.125 molar hydrochloric acid. Okay. So this will be the other question on this part of the quiz. I'm going to take this, move it over a little bit, and let's grab this whole question and talk through it here. I'm going to assume that you've already taken a moment and paused and thought about that. So let's jump into this problem. The equivalence point is where the number of moles of H plus is equal to the number of moles of OH minus. Right? We've thought about before how a solution that's acidic has an excess of H plus ions, or in other words, an excess of protons. And we've talked about how a solution that's basic has an excess of OH minus. Okay? So with that in mind, we've also talked about how an acid-base reaction can also be called a neutralization reaction, because in this case, we are reaching a neutral pH, right? Not acidic, not basic, because we have neither an excess of H plus nor an excess of OH minus. Okay, at the equivalence point then, this is where we're going to know that the number of moles of H plus are equal to the number of moles of OH minus. So then, in that case, we need to figure out one of these two numbers, right? That's probably a good place for us to start. We need to figure out how much of this sodium hydroxide we need in order to reach the equivalence point. So let's figure out how much of the other species is present at the equivalence point. To do that, let's take note of the fact that we already know a couple facts. We know that the volume of the hydrochloric acid present is 150 milliliters, or in other words, that will be 0.150 liters. I'd like you to take a second, if you're not sure about that, work out the conversion factor, right? Here all we would do is include the fact that 1 liter equals 1,000 milliliters. Okay, so I want you to take a second and do that if you're not comfortable with that. We're going to go ahead and move on and look at the concentration here. Now let's go off to the side here and just refresh ourselves. I want you to remember that molarity, which has the symbol capital M, is equal to the number of moles of solute divided by a certain volume of solution in liters. Okay, so for the value that we've been given here, we know that there's going to be, where's the mouse, 0.125 moles of the solute, which in this case is the hydrochloric acid, dissolved in 1 liter of solution. So, whether by looking at the units here, or by looking at this equation over here and rearranging it, so let's actually do that real quick. We could rearrange this to say that the number of moles of hydrochloric acid is going to be equal to the concentration of that hydrochloric acid solution times the volume of the solution. Okay. And in fact, instead of HCl, let me say volume of solution. Okay, so good deal. Let's plug in some values here. Seems to me like we could say that the number of moles of hydrochloric acid is going to be equal to 0.125 moles HCl, which is the unit that we're looking for, but it's currently divided by 1 liter of solution. But we know the volume of solution, right? We know that there are present 0.150 liters of solution. So what I end up getting here, let's go ahead and see what that is. It's going to be 0.125 times 0.15, and I get this value, 0.01875. Okay. So let's put that down here. 0.01875 moles of HCl. Okay, well good. We know the number of moles of HCl, but what we were really looking for is the number of moles of H+. But we know, right, that HCl is a strong acid, meaning it splits up completely. So 1 mole of HCl in aqueous form produces 1 mole of H+. So that means, right, hopefully we can see from that that the number of moles of H+ is going to be equal to the number of moles of HCl. So that's going to be equal to 0.1875 moles. Okay? So with that, we now know what's happening at the equivalence point. At the equivalence point, there are 0.01875 moles of H+, and that must be exactly equal to the number of moles of OH-. So let's come down and copy that down. We know that the number of moles of OH- at the equivalence point has to be equal to the number of moles of H+, so it's also equal to 0.01875 moles. But we also know that sodium hydroxide is a strong base. So in other words, 1 mole of NaOH produces 1 mole of OH-. In other words, we can also say that the number of moles of, here we go. The number of moles of NaOH is equal to the number of moles of OH-, which is 0.1875 moles. Okay, well, we're nearly at the end of the calculation. What were we actually asked for? We were asked for what volume of this concentration solution of NaOH. Well, we know the concentration for molarity, we know the formula for molarity. Let's copy that one more time and bring it down here with us. Okay, so with this, we should be now equipped to answer that question. Let's rearrange this one more time. We're starting with this form of the equation. The concentration of the NaOH solution is equal to the number of moles of NaOH divided by the volume of that solution. Well, let's rearrange this. I could say that the volume of solution times the concentration of the solution of this NaOH solution is equal to the number of moles of NaOH, right? But this is not exactly the form I'm looking for. I want to solve for volume. So now, let's get that by itself. This is going to be equal to the number of moles of NaOH divided by the concentration of the solution. Okay, well these we now know, right? So let's go ahead and solve this. The volume of the NaOH solution that would be needed is going to be equal to 0.01875 moles of NaOH divided by, and what's that concentration? Well, up here, that's going to be 0.5 molar. So this is going to be 0.5 moles NaOH per 1 liter solution. And all I did here is break apart the definition of molarity. Okay, so there's a fraction down there, but this would be just the same as saying 0.01875 moles of NaOH divided by 0.5 molar NaOH. Okay, and in either case, what that will end up being is 0.01875 divided by 0.5, so that value that value times 2, so we would get, oh, come on. Okay, 0.0375 liters or, in other words, 37.5 milliliters of the NaOH solution. And this is how many would be needed to neutralize the amount of HCl solution that we started with. All right, so thank you for watching through this one. I've got just a little bit more to record here, so I'm gonna stop this one and get onto that, and we'll go ahead and wrap this up. Thank you for watching.